All right, so the recording has started. All right, well, listen, I do want to get started and talk about the fundamental theorem of calculus. This late in the semester, and we're dealing with the fundamental theorem. That's kind of special. But one thing I want to point out is, tell you what, let me take it across to the text. I've got a webcam over here on a text, a bit of the book. Now, I don't know if you're able to see that clearly. But it's got a fairly close up to the fundamental theorem of calculus. And it does say part two, but it's a key point that this is how things are defined. This is a formula that gets you how you use the tool. And notice that it's what it's saying. Lowercase f is a function. It's continuous on the closed interval a to b. All right? So cap f is the antiderivative of it. It says any antiderivative of it. So notice that means any antiderivative. If it's an antiderivative, notice we're saying usually plus c because it could be a lot of different constants out there. But then you're taking the cap f of b minus cap f of a. They're both the same function, and therefore the plus c that you add is going to be subtracted off every time. So every time you've got a definite integral where you've got numbers a and b on the integration bar, you don't have to put the plus c on there because it's subtracting off every time. If it's indefinite, you still need it. But if it's definite, you can clear it off. Okay? So the integral of small f of x dx, the dx is crucial also, you guys, for some important stuff that's coming, equals the antiderivative at b minus the antiderivative at a. All right, so let me give you a couple of examples of that now, and go over to my, let me go to the iPad here. All right, so one of the things I've written up here, well, first of all, let's take a look at it. I've got this function. I'm over here right now. This is what I'm looking at. F of x equals 2 is the function we're talking about. All right. So we're talking about f of x equals 2. And f of x equals 2 is the graph of that is the line y equals 2. So there is the line y equals 2. That is f of x equals 2. All right. Now, when we integrate, what we've been doing with the problems in a variety of different sorts, when showing velocity and distance and a combination of different things, the antiderivative is the area under the curve. All right? So the area under the curve. What I've got drawn here is I'm going to take the antiderivative of 2 dx, because it's a function in terms of x, even though there's no x there. It's a function in terms of x. X is the variable of concern. So when any variable shows up, it's going to be x. But 2, the function is 2 from -2 to 3. All right? So what that's got is, we're talking area under the curve. So what I want to do in the graph is I want to show you this. So that means the area of our function from under the curve from -2 to 3 is going to be this area right here. And that is 2 high and 5 wide. So the area of that thing is 10. Okay? So the area is equal to 10. And notice, in order to use the formula that we have here of a to b of little f of x dx is equal to cap f of b minus cap f of a. All right? So what we're doing here, we need cap f. Every time you take an antiderivative, you need cap f. So looking at little f of x is 2, then cap f is the antiderivative of it. What did you have to take the derivative to get to? 2x. And like we've been saying, 2x plus c is going to be the norm that you're going to need to write if it's an indefinite integral. But again, we got a plus c, got the same function here. You're subtracting the c away. So you can disregard it. So 2x is all we're concerned about without the c. Okay? Without the plus c. So here's our integral. We've got this function right here. Here's our integral I'm asking you to take now. And this is what you're going to be asked to do consistently through the semester, the rest of the semester. the integral from -2 to 3 of 2. The answer should be 10. The area here is equal to 5 times 2, which is 10. All right? But what do we get? So we got to take f, cap f of b. Cap f is 2x, and we're going to stick b in it. This is b is 3. B is 3. So I've got 2 times 3 minus cap f of -2, which is 2 times 2, -2. Do you see 10 coming there kind of briefly here? That you end up with 2 times 3 is 6, and -2 times -2 is 4. We end up with 6 plus 4 is 10. All right? And the idea is that does concur with what we got for the area under the curve. But the integration thing that we're talking about is we went with 2, converted it to 2x, okay? And I want to show you some notation that is traditionally used in math to recognize this. So if we had, let's go back to that original function that I had here. If we've got the integral of -2 to 3 of 2 dx, the typical notation that's been used, the text uses something a little different, but I'm going to stay with my older fashion because it's simpler. But the integral is 2x, so it's 2x from a to b. That little bar afterwards gives us a reminder of what our variables are, what the a and b are. So then that gives us 2 times 3 minus 2 times -2, which is 6 plus 4, which is 10. Okay? So the notation used, what they do in the text is they make a full bracket out of this. They put a bracket behind and a bracket before like that, and then put the a and the b afterwards. I'm saying if you want to do that, feel free. That's consistent with what the book shows, and you might see it if you do it online. But I am totally wonderful with the idea of just this equals 2x from -2 to 3, which is 6 minus plus 4, whatever, equals 10. So showing you're working on that line. Any questions about that at all? Hey, and if you would, get your calculators out. I asked you to bring them. And while you got it, why don't you get your calculator out and let's do that integral we just did, okay? So I've got a TI-84 here. If you got a TI-83 or 84, do you mind sharing, what do you guys have for, say out loud, unmute yourself for a second and just say you got a TI-83 or a TI-84, or Desmos.
I got an 84.
84?
I got 84.
84.
84.
Okay. All right, good, good, good. All right, well then, so all of you said 84, correct? I think you did. All right, and if you do, then you're going to have the integration bar show up when you plug it into your calculator. So what I would like you to do is right now is go ahead and hit your calculator and hit the math key, and then hit number 9. Number 9, or you could go the arrow down to 9. That's FNINT. So it looks like this. This is the mode FNINT with a parenthesis, okay? And on the 83, and the way my calculator is set up right now, if you hit enter on that, you get the integration bar on the 84, I believe. Mine, the way this is set up on my calculator, I have this on my calculator, all right? If you have that, then you've got to type in the function name. And so if you've got the integral going on, then we're going to plug in the function that I had here, which is -2 to 2, 3. So if you would, type in down at the bottom there, -2 down here, and then push an up arrow and plug the 3 in there. And then down here where there's parentheses, I just like you to put a 2. Put the 2, that's the function. And then outside there's a D out there with a blank, and put a dx out there. So 2 dx it should look like that when you're done. And go ahead and hit enter, and the answer should come out to be 10. And for me, I've got the FNINT. If you're ever dealing with that, then what I've got to do is plug in here what the function is. It's in terms of x, and it's going from -2 to 3. So that's what I got to plug into this puppy. So I've got 2 as the function, comma, in terms of x is what you put the d in, dx out there. And then I've got -2, comma, to 3. Close parenthesis, and I get 10. Everybody get 10 on your calculator? Anybody not get 10? Why don't you say that? Okay, good. All right, listen, if that's the key point of using the calculator to verify your answers, I'm going to ask you to be able to do it longhand like we just did with that 2, convert it to 2x and use the plug in -2 and 3, but you can verify your answer using the calculator. And if you haven't practiced it yet or seen my videos or the videos, the YouTubes on the computer, on As You Learn, to make sure you use those from last week and look at those and practice that on your calculator, get that down. Okay, now what I want to do kind of quickly though, I want to show you this. It's kind of an important one to recognize what happens when you got the variation above and below the x-axis. So what I've done is I've shown a graph here. I've got f of x equals x minus 2. You can see that. And if anybody's got anything to say, please speak up and interrupt. I can't see your faces or anything right now, so it's just a matter of going unless I hear you stop me. All right, so here's the deal. I've drawn the graph of x minus 2. Y equals x minus 2. That means the y-intercept is -2 down here. And the x-axis over 1 up 1, continue out here. There's the line x minus 2. All right? And what I want to do is I want to show you guys, if we take the area that's just above the curve, that would mean from 2 to 6, right? Then that would be the area under the curve there. And this side goes up to 4. I got a little careless with my coloring. You know, I never could stay in the lines real good. That was always been a good one for me. That's kind of an interesting little moment. But we've got 4 there, and then we've also got 4 here between 2 and 6. So the area of that is 1/2 base times height. 1/2 4 times 4. That ends up giving us 1/2 of 16, which is 8. So the area in here is 8. All right. So I just want to do that on your calculator if you would. Do the integral of x minus 2 dx. So that's got to be inside the parentheses. And we're going to go from 2 to 6. And we got the answer of 8 a second ago. Let's check and make sure we do that. All right. So I'm going to do the integral. I'm going to do math 9. My function is x minus 2. Fat finger there. Okay, so I got x minus 2, comma for me. And it's going from that. I need the x again, the variable of concern. That's the dx. And then I'm going from 2 to 6. 2, comma, 6. Close parenthesis. And hit enter. And I do get 8. Everybody see an 8 on that? Okay, good. Now, we'll do that one more time. Set it up, but this time we're going to get this area right here. The area that's below the x-axis. So that integral is going to be going from 0 to 2 of x minus 2 dx. And that's 2 by 2, 1/2 base times height. 2 times 2, that's 1/2 of 4 is 2. So this is 2, but look what happens here. If you were asked what the area of that triangle is, the answer is 2. But when you integrate, it's below the x-axis. Watch what shows up on your calculator. The area is 2, but the calculator shows below the x-axis by making it negative. So I'm going to do again, math 9, x minus 2. Do it please on your calculator, right? Comma x, comma, okay, and now we're going from 0 to 2. We've got 0, comma, 2. And on your integral, put 2 down there for 0 for A and then 2 for B. Close parenthesis. You see that minus sign in front of the 2. Okay? So as verification of this, now let's do the one last one. Type it in again. This time go 0 to 6. Go the integral again, 0 to 6. So I'm going to do math 9. X minus 2 is going to be in the slot there. So x minus 2, comma, and put the x out there behind the d. And then we're going to go from 0 to 6 this time. So I've got to go comma, 0, comma, 6, close parenthesis. And notice you get 6. that added together the 8 that you had and the -2 that you got from the lower part, okay? So I think that's worth knowing, that that is a key feature of the moment. And now really quickly, I'm gonna do the antiderivative by hand using the fundamental theorem of calculus. So this time we're going from 0 to 6, and we got the answer, it should be 6, of x minus 2 dx. All right, so the way I said to write that before is to use the notation. I'm going to go ahead and get the antiderivative. The antiderivative of x is x squared over 2 minus 2. The derivative, the antiderivative of that is minus 2x, right? And that we're taking on the integration bar between 0 and 6. I'm not sure if that's got the type of integration bar, but it's saying where the variables run to, the a and b. So what we got to do now is plug in the 6 and plug in the 0. And notice, you guys, both of the variables have an x. So when I plug in 0, that second answer is going to be 0. So the key thing is plug in the 6. That gives me 6 squared over 2 minus 2 times 2. That's the f of cap f of b minus cap f of a is 0. So check it though. Sometimes if x is up in the exponent, that means it's not going to be 0. It means it's going to be 1, you know. So that ends up being 36 over 2, which is 18 minus 4. 36 over 2 is 18 minus 4. Oh, 2 times 6, you guys. You saw it and didn't say anything. Why the answer wasn't coming out quite right, and it caused me a little concern. So 18 minus 12, which ends up being 6 that we were looking for. Okay? Everybody see that? Comfortable? Okay, there's a couple more things I want to say. And let me come back to looking at me now on the screen. All right, so let's get back here to me. All right, so now what I want to do is I want to show you something. I want to remind you of something. Another aspect of the antiderivative. The thing we looked at right there, notice it said it was part 2. Part 2 was how do you do the calculations and stuff. Part 1 is a little bit different in the text, but it's talking about, it's referring to the fact that what's happening, this is the reminder, that a fact that I want to make sure you're clear on. That remember, when the area under the curve, for instance, when we did this problem the other day, when I did this in class, and we were working with the velocity on the side, and these are time in seconds, and we had this going, that we ended up finding how far we went by getting the area under the curve. And we did rectangles, you know, we did rectangles from here to here, and from here to here, etc., and all this kind of stuff. But the main idea was that we were finding the area under the curve as a means of estimating how far we traveled. So we added all these rectangles up, and then I went above the x-axis and got another set, and we went up here, and I should use a different color maybe, but no, right now I'm just going to do this and show you that. Then we got these rectangles. That whole, if you take the top rectangle area and subtract the bottom, you get the difference between those two, and that ends up being this area in here, which is error. But the key thing that we were talking about was this graph is the velocity. It is the velocity. It's a rate of change. It's a rate of change of how where your position is. And as a result, the area under the curve turns out to be the distance traveled. How fast you're going is a rate of change, and what's under the curve is a distance. So this ends up being distance down here, okay? So another situation, there's a couple problems that I give you in Sapling, that it's a word problem. And one of the things, it's a rate of change of how fast the water is flowing into this reservoir, okay? So you take the antiderivative of it, this function, how fast water is flowing into the reservoir, it's the rate of change of water flowing in. So the antiderivative of it is how much water's in there. How much water's in there from the time 0 is what the problem's going to be to how long it was running in there. There's another one in sapling that's got to do with insect population. It's growing. The rate of change per day of insect growth. Okay? Well, what's the antiderivative of that? Growth, the rate of change is on top. It's the graph, it's the, so to speak. When you take the antiderivative, you find the area underneath it, and that is actually the number of insects. So the rate of change gives you the, the antiderivative of the rate of change gives you the actual change in how many, whatever it is, how many feet you in, how many liters poured in, how many insects there are. And that's what the first part of the fundamental theorem, we'll talk more about that tomorrow and stuff. But the main thing is dig into the problems, use that fundamental theorem, and practice the problems of using the fundamental theorem, and get the A and B straight, and make sure you're conscious of the fact of using the rules and maintaining antiderivative is what you're accomplishing each step of the way. All right? Any questions at all about that? Let me come back to the screen here and come back to, anybody have anything at all? Questions or anything? Okay, tell you what, then what I'm gonna do, I'm gonna go ahead and get into the test, okay? If any of you have questions about that, we'll address them now, and that's what I'm gonna work through right now. So I'm gonna go back to my iPad and work through several problems on the test. Okay, let's clear that one off. And if you want to cut away, you're welcome. But if you want to stay, I'm going to go through each problem of the test and make sure you're solid on it. There won't be a rewrite on this portion of things, but that's the. I'm going to go through it now to make sure you're solid on the situation. I tell you what, though, if you do apply yourself and you work on a particular problem that you did wrong and turn it into me, take a picture of it, let me see it, I will probably acknowledge something, particularly if you miss several questions or something. Show your work, make it clear that you understand it, and I'll take a look at the idea of maybe giving a little bit of credit, but it's going to be teeny weeny, okay? I'm giving you the answers, so make sure you're solid on it. Do it yourself and be confident with it, all right? All right, so if you have your test nearby in front of you or something, the first question was f of x equals x to the third minus 6x squared. And if you guys notice, I don't know if you saw it, recognized it, this is for number 1 on the exam 3. But the thing I say on that first line is include using the first derivative test. And several of you left that off. Several of you did not use the first derivative test, which meant check on each side of the critical point and see if it's increasing or decreasing. The graph is increasing or decreasing at that point. So that's a key part of getting a completely correct solution to this problem. So what I want to do is let's take the derivative of it and do the first derivative test. So the derivative of this, I hope you're confident. The vast majority of you, I think everybody, got the derivative correct. But this is what bit you a couple times, is factoring it. You got to make sure you factor it and you count both values, an x that's out there and the other, as critical points, critical values, so critical points. So what we've got common here, there's a 3 and an x. A couple of you just took the 3 out, but there's a 3 and an x, and what's left is x minus 4. So, and this is where a couple made a mistake also. The idea is that you've got to take into consideration when you set this equal to 0, that you've got 3x equals 0 and you've got x minus 4 equals 0. This means x equals 0 and x equals 4. So on a number line, you've got 0 and 4. And again, most people picked the values that were closest nearby, minus 1, 1, and 5 was an integer there. And plug those in, but what you're trying to do is determine what is the slope on each side of these numbers. So you got to plug it into the derivative function. So when I plug in, so I need f prime of 0. And that gives me 0 minus 0, which is 0. So what is that? No, it doesn't, does it? Yeah, it does. We don't want f of 0. Ha! Okay, so thank you if you're smiling. If you're not smiling, just find the reason to. Okay, so this, we need -1. What we need is f of -1. F of -1, and that is not 0 minus 0. Okay, so f of -1 turns out to be 3 times -1 squared minus 12 times 3. I could have plugged it into the factored equation as well, but I end up with here with 3 times 1, which is 3, minus 36, which is minus 33. Something wrong here? Oh, boy, you guys, somebody needs to speak up here. I plugged a 3 in over here. So I needed a -1 here. Okay, ready? I'm going to start this over in just a minute. So I end up with -3. I have +3, minus times a minus equals +12, which equals positive 15. So that gives us a positive on this side, positive 15. Then we need one in between. That's f of 1, f prime of 1. Plug in 1, so we got 3 1 squared minus 12 times 1, which is 3 minus 12, which is -9. That gives us a minus value in here. It comes down. All right. And then the last one, I'm going to try 5, f prime of 5. Let's do the factored one this time. That gives me 3 times 5 times 5 minus 4, which gives me 15 times 1, which is 15, which is positive. That means it goes up. That indicates at 0, we've got a max. We've got a local max. And at 4, we've got a local min. They come together down there and they come together up top. That is the first derivative test. Therefore, and then we plug in 0. Now we got to figure out the value of it. So we give the coordinate. We got to plug that back into the original function. So we get 0 cubed minus 0, which is 0. So the first one is 0, 0. And that's a local max at 0, 0. So another way to write it is local max equals 0 at x equals 0. And the other one is if we plug in 4, we've got f of 4, which is in the original function, 4 cubed minus 6 times 4 squared. That's 64 minus 96, which is -32. So the other point is going to be the local min at 4, -32. Or another way to say it is local min equals -32 at x equals 4. Remember, what you're finding, the local min is actually what's the minimum value of the function. The max is what's the maximum value of the function. And graphing it on your calculator is, it's the local though. So it's just a high point, but then when it takes off, it goes up beyond it. And it's a local min, it takes off beyond it when you go down to the left. Any questions on that 1A? Okay, look at 1B. So I've got this kind of drawn out, and what you can do is get it on your calculator, and take a look at it and recognize this is the situation. I've used the calculations, I've used the first derivative test to determine what the slope is on this side. So I verified that it's positive, it's increasing here. It's negative, it's decreasing here because of these numbers. I got this value over here. This is what, positive 15? So I can show you the value that lets me know it's increasing. I got a positive 15 as the slope. And at 1, we got a negative, what was it, -9? So I did the calculation and I got a negative value. If you just look at the graph and give me the answer, that isn't the complete statement. Something I had said early on, I said at the top of the test also. The best answers will be those that use math and not refer to just the graph of a function. Okay, so the answers for increasing, this is going up to 0 from negative infinity to 0, and this is going from 4 to infinity. All right, so we've got in between coming down. This is up, this is up. So we've got increasing from negative infinity to 0, open on both ends because you don't count the endpoint in both cases, union 4 to infinity. All right, you don't, again, it's open intervals on both, and the decreasing interval is in between 0 to 4, open intervals again. You don't count the endpoint because it's not increasing or decreasing at the endpoints. Slope is 0. Questions on number 1, A. Okay, let's go on to 2. 1B. 1B. Let's go to B, or not to B. All right, so for part B, that was B. B was increasing intervals, decreasing intervals. C, concave up and down. Okay, so we've got the graph here, and several of you just pointed to it and said, there's that, you can see it's concave up and concave down. I want you to be able to indicate to me, show me, calculate that it's where it is. You know, this is at 0, this is at 4. Where it is it concave up or concave down? The second derivative, we had the original function was f of x equals x to the third minus 6x squared. So f prime of x equals 3x squared minus 12x, and f double prime of x is equal to 6x minus 12. Therefore, the second derivative, when we plug it into the second derivative, that is an indication of whether it's concave up or down, positive or negative. So we plug in 0, f double prime at 0 gives us 0 minus 12, which is minus 12. That's minus. That means it's concave down here. And f double prime at 4 gives us, you plug in the critical point, and that is that's the second derivative test, but you can use any point over in that region and it'll work. But the second derivative test is you plug in the actual critical number. We end up with what? 24 minus 12 equals positive 12. Therefore, that's at 4, its second derivative is positive, therefore it's concave up. Notice concave down and concave up switch right there. And that is where the point of inflection is. But the answer to part C is that the concave up interval, and you got to make sure you can handle writing an interval notation, you guys. If you write with inequality signs, that's fine. But you don't do both. Don't do inequality signs and the brackets. So concave up was what I gave first. That's this one over here. And it goes where? Where does this equal 0? So we've got 6x minus 12 equals 0 will give us where the point of inflection is. 6x equals 12, x equals 2. So the concave up starts at 2, it's halfway between 0 and 4 is a good help, 2 to positive infinity, and concave down ends at that 2 and goes to negative infinity to the left, okay? Concave down is over here, concave up, and the point of inflection is where it changes. So, and then point of inflection, this I accepted as a way to get your x value for calculating the point of inflection. So point of inflection is actually the coordinates of this point right here, and that's at x equal 2. So we need f of 2, and that gives us 2 to the third minus 6 times 2 squared equals 8 minus 24. Is that right? 2, 8, yeah, that equals negative 16. So the coordinates are 2, negative 16. And the point of inflection, it's negative 16, but the point is actually 2 and negative 16. Usually the 2, if you're ever asked for just give one value, it would be what the x value is. It's 2. The point of inflection is the x value is 2, but the y value, a complete answer is 2, negative 16. Okay, answer to number 1. Any other questions? Okay, let's look at number 2. All right, number 2, find the absolute max and min of f of x equals x to the third plus, minus, okay, minus 3x squared plus 20 on the interval negative 2 to 2. Again, I wrote it with inequality signs on the test, that it would have been the same as if I did this, you know. On the test, it says this. Both of those mean the same thing on that interval. So what we've got to do is take the derivative, see if there's any critical points in between these two values in the interval. And all we got to do is check the endpoints and the critical values. There's a handful of you that checked every possible integer in between. And I took off a little bit. That's not what this situation's about. That's not what we were talking about. Derivative approaches, trying to get across. For you to do this in Calc 2, you need to be able to know the efficient way to do this. So you check, so take the first derivative. You get 3x squared minus 6x. And then you're going to set that equal to 0 to find any critical values. So what's common is 3x. And there were a couple of you that got minus 6 here. And that bit you, because that changes your answer. You did everything else correct, but it throws things off severely, you know, when you're solving the problem and you don't factor it correctly. So make sure you get that right. So the two critical values are 0 and 2. So we need to check endpoints, negative 2 and 2, and that is one of our critical values, so that's gobbled up. But 0 is a critical value in between negative 2 and 2. So what we need to do is check out f of negative 2. We're trying to find the max value of the function. So it's f, not f prime. Handful of you plugged it into f prime, and that is not the correct solution. Then we've got f of 0 and f of 2 are the 3 points we need to check. The 2 endpoints and any critical point in between, that's them, and plug it back into the original function. So we get negative 2 cubed minus 3 times negative 2 squared plus 20, which is negative 8 minus 3 times 4 is 12 plus 20, and negative 20 plus 20 is 0. All right, and then we've got plug in 0. You get 0 minus 0 plus 20 equals 20. And we're looking for the minimum value and the maximum value of these values I'm circling. Plug in 2, we get 2 cubed minus 3, 2 squared plus 20, which is 8 minus 4 times 3 is 12 plus 20, which gives us minus 4 plus 20 is 16. The maximum value that we attain is 20 at x equals 0. Absolute max, because this is a closed interval. You've got a starting point and an end point. That first function we were doing where I would find local max and min, it was going on forever. There was no limitations. It was an open interval, forever, infinity. This is limited. If it's limited, the extreme value theorem tells you there's got to be a max and there's got to be a min. So absolute max is the 20 at x equals 0, and absolute min equals the smallest number is 0 at x equals negative 2. Got it. Questions? Okay, let's go on to number 3. All right, number 3. Let me get a new situation here. All right, so for number 3, I don't think I numbered that number 2, but this is number 3. This is L'Hopital consideration. So the idea is the limit as x goes to 0 of 5x minus sine x over x. Several of you immediately jumped in and took derivatives, okay? And that's not right. The thing is to use L'Hopital's rule, which means take the derivative of the top and the derivative of the bottom, if you want to recheck it, is first check and see if it's got an indeterminate form. So as x goes to 0, plug in 0 for x, and you get 0 minus sine of 0 is 0 over 0. That's 0 over 0. That's the indeterminate form that says yes to L'Hopital's rule. Therefore, this, and several of you left off equal signs all the way through. You need to catch it. Limit, this is equal to the limit as x goes to 0, the same limit, but you take the derivative of the top and the derivative of the bottom. A couple of you just said the derivative of the whole thing, and that's wrong. The notation was wrong. The derivative of the whole thing would be the quotient rule. So it's the derivative of the top over the derivative of the bottom, which is going to be 5 minus cos x over 1. Plug in 0 here now. We don't have to write limit. We do need it previously. We get 5 minus the cos of 0 over 1 I can ignore, right? And that's equal to 5 minus 1, which is 4. So the answer to the question is 4. And it is, and you got to use the check for L'Hopital's rule first, right? All right, that's 3A. 3B is the limit as x goes to 0 of sine x over e to the x. All right, so on this situation, what we've got is a matter of plugging in the 0, just check it out first, and you end up with, if you get sine of 0, which is 0, and you get e to the 0, which is 1. And there are several of you that got this. The answer to that is 0. You just answered the question. The answer is 0. You're done. Several of you went on, used L'Hopital's rule and did it. This does not qualify as using L'Hopital's rule. So as soon as you get to 0, you're done with that one. That's the answer to the question, okay? Let's look at C. The clock's ticking here. I need to keep moving. C is the limit as x goes to infinity of x squared over e to the x. All right, and you check that first, and as x goes to infinity, this is going to infinity on top, and it's going to infinity on the bottom. There's an indeterminate form, L'Hopital's rule. Take the derivative of the top, and this is equal to the limit as x goes to infinity of the derivative of the top over the derivative of the bottom. Plug in infinity. Well, not plug it in, but as x goes to infinity, this goes to infinity, and this goes to infinity. L'Hopital's rule, do it again. That's equal to, equal sign's important. The limit as x goes to infinity of the derivative of this, which is 2 over e to the x. Now, when I plug in infinity, notice that there's not going to be an infinity on top. I'm done. A couple of you took the derivative of the top and got 0 for your answer, but it was for the wrong reason, okay? You plug in as x goes to infinity on this thing now, you get 2 over this thing that's going to infinity, all right? It's going to infinity, which indicates that's getting huge on the bottom and it's a fixed number on top. That's equal to 0. Several of you wrote this as 2 over 0. You included 2 over infinity, then you put 2 over 0. Somehow, I took off for that. That was not appropriate. If you put 2 over infinity, I didn't count that wrong. It's x, the denominator is going to infinity, and the idea is this problem is going to 0. But those of you that put 2 over 0, somehow that slipped in there. That's not correct. It's going to getting huge, not going to 0 on the bottom, okay? And then D, the last one here, turns out to be the limit as x goes to pi. A little different. It gives you a constant you got to go to, 1 plus cos x over 2 sine x. Sine of 2x, excuse me. Okay, over sine of 2x. All right, so let's plug in pi, see what we get. I get 1 plus cos pi over sine 2 pi. Well, 1 plus cos pi, remember where pi is over here. Cos is x, it's -1. 1 plus -1 over cos of 2 pi is right there. sine of 0, sine of 2 pi is 0. You get 0 over 0. That means you can use L'Hopital's rule, which means you take the derivative of the top. That is equal to, an important part of the answer is equal to. Also, the limit is an important part of the answer. That's got to follow it along. The derivative of 1, several of you put 1 here, 1 minus sine. The minus sign was wonderful. The antiderivative of cos, what got you to cos was actually the antiderivative of cos is, oh no, you're taking the derivative. We took the derivative. Derivative of cos is negative sine. Derivative of 1 is 0. Derivative of cos is negative sine x, right? Over, and down here, you're taking the derivative. That means you got to use the chain rule. Derivative of sine is cos, 2x goes there, times the derivative of 2x, which means we get, this then becomes, that becomes the limit as x goes to pi of negative sine x over 2 cos 2x. All right, and now plug in pi. Here we get negative sine of pi over 2 cos of 2 pi. Sine of pi, we're over here. The sine is y. Y is 0. So that equals 0 on top. On the bottom, we've got cos of 2 pi is over here. Cos there is 1. That's 2 times 1. That's equal to 0 over 2, which is 0. Done. Okay? And now I need, so the answer is 0 on that. Make sure you cover all bases. Let's get the last one. Okay? I think this is the one that most people got the most right out of all the questions on the test. And that was this. We had but there are a few of you that made a mistake that there's a wall here. And a couple of you used the formula 2x plus 2y, and that bit you, okay? Because the answer comes out, it's not 4 sides, there's only 3 sides. So the fencing equals 2x plus y, and that equals, we were told that there are 1,600 feet of fencing. So we've got the amount of fencing, the formula comes to 2x plus y equals 1,600. And then we've got the area formula that we're concerned about. What is the max area? So we need to take the derivative of this and find a max. So I'm going to solve for y on this situation. I get 1,600 minus 2x. Therefore, a equals x times 1,600 minus 2x, which is 1,600x minus 2x squared. Done. Area is the function. Now we got to take the derivative of that. We get 1,600 minus 4x. Set it equal to 0, and we end up with 4x equals 1,600, x equals 400. Plug it back in here, and you end up with y equals 1,600 minus 800, which is 800. Y is 800. Therefore, area equals 400 times 800, which is 32, and there's 4 zeros. There were a couple of you, and it's feet squared because it's area. Max area. Okay? Any questions on that? You got one? Somebody spoke up. Did you say you smiling? All right. You okay? All right. Well, listen, if you got any other questions or something, I'm going to be back at 2 to 3. Feel free to call during my office hours if there's any other questions about the test. But get going on the sapling. The sapling from section 5.3, we got a week, I'm giving you till the test to do it. And that's coming up pretty soon, Monday. So get going. If you got any questions, let me know, all right? Be well, you guys. Thanks for showing.
Thank you.
I'm going to